This program is brought to you by Stanford University. Please visit us at stanford.edu.
Okay. A periodic line can either mean particle really moving on a circle, or it could just be a rule that you have a finite length of line, and your rule is whenever the particle gets to this point over here, it instantly reappears at the other end of the line. Just a rule that you could wrap it in a circle if you wanted to in your mind's eye, but that doesn't necessarily mean that the object is moving in a circle. It's moving on what is called a periodic line, so that motion is periodic. If you disappear out this end, you reappear on this end. Under these circumstances, the analog or the analog statement for quantum mechanics is that the wave function psi of x should be periodic. Psi of x, let's call this distance L. Psi of x should equal psi of x plus L. That's the notion of a periodic wave function. The infinite line, where the line grows to infinity, is the limit of a periodic line where the length goes to infinity. So you can study quantum mechanics or waves, any kind of field theory, as the limit of a field theory or a Schrodinger equation or whatever it happens to be, even just particle mechanics, on a periodic line in the limit that the line gets infinite. For ordinary classical particle mechanics, there's not much advantage in thinking about it periodically, but in quantum mechanics it is very, very useful to begin with a periodic line. Now, since psi of x has to be equal to psi of x plus L, that has, as was pointed out a moment ago, that has implications for the spectrum of momentum, for the possible eigenvalues of momentum. Remember, the wave functions for a momentum eigenstate are e to the I px. Incidentally, this is not quite the ortho, p being, oh, this is not right, is it? I'm missing something. H bar in the denominator. And we often call that e to the I kx. K is just momentum divided by h bar. I think I'll use the k notation. Or you can simply work in units where Planck's constant is equal to 1, and then k and p are the same thing. Okay, this is the wave function, but it's not properly normalized. Remember, the rule for a normalized wave function is that the integral of psi star psi should be equal to 1. That's basically the statement that the total probability of finding the object someplace should add up to 1. If I take this wave function with p as a parameter and I multiply it by its conjugate, psi star psi would just be equal to 1. And if I then did this integral, then, oh, I'm sorry, you know what? I want to go back one step. I want to think of L as equal to 2 pi r. I want to imagine that it is on a circle. This is just for notational convenience to think of it as on a circle. And then this would not be true. Psi star psi is 1, but then the integral over x from 0 to 2 pi r would not be 1. It would just be 2 pi r. So what I would do to fix it is I would divide the wave function here by the square root of 2 pi r. Then, when I did the integral of psi star psi, for each of these momentum eigenfunctions, they would be normalized so that the total probability would be equal to 1. Everybody understand why I put square root there? I put square root there because when we multiply psi star psi, the square root from here will combine, well, the square root from here will be squared, and the integral will be 1 instead of what I have there. Okay, I only mention this because you're going to see 2 pi's all over the place. This is where they come from. They're not very interesting, but that is where they come from. Now,
or you could say that the definition of length has a square root in it.
Okay, however you, well, the definition of length doesn't have a square root. The definition of the wave function has a square root.
No, I mean, the reason you chose the square root there is that you're trying to get unit length.
Unit length for the vectors, yeah, for these vectors. Yeah. Not for this length.
No.
Right, that's right. That's right. Once we have that, we look at the individual wave functions, these wave functions for given momentum, and we require that they're periodic. That says that k times 2 pi r, that's the value of the exponent here when you've gone one full cycle around. That must equal 2n pi. In other words, if the wave function over here, let's say the wave function over here is 1, then over here it will contain the factor e to the I k, and then x will equal 2 pi r. If the wave function is to be periodic, then e to the I k times 2 pi r must equal 1, and the only way that that can happen is if 2 pi r k is equal to an integer multiple of 2 pi. All right, so that would just say that, that the length r times k must equal an integer. Or that the eigenvalue k, this is the eigenvalue of the momentum, or strictly speaking, it's the eigenvalue of the momentum times divided by h bar. The quantity k is quantized in units of n over r. All right, now, this means that if I were to plot on the horizontal axis here the spectrum of possible values of k, I'm not making a graph, I'm just going to put down all the possible points k, that they form a discrete collection with a spacing which is 1 over r. So, there they are. Those are the possible values of k, starting at 0, going off to negative infinity, going off to positive infinity. Okay. And the separation between them is 1 over k. Sorry, 1 over r. So as r gets bigger and bigger, the spacing between different values of k, neighboring values of k, gets smaller and smaller. And eventually we can say that when the r-axis gets infinitely big, the spacing between neighboring values of k shrinks to 0, and we can say just about every value of k is possible. Or there's no value of k which isn't arbitrarily close to an allowable. They get dense. They get dense. We might as well just say every value of k becomes possible. That's in that limit. Now, next step. To go to the limit in which the eigenvalues become very, very dense. Oh, before we do that, let's just notice that without proving it, since we've already proved it, since these wave functions are eigenvectors of a Hermitian operator, for different values of k, they must be orthogonal. Okay? This is true if we calculate the integral from 0 to 2 pi r of e to the I k x times e to the minus I, let's call it k prime x, where k and k prime are allowable values. Then this integral is 1, sorry, we have to put a 1 over 2 pi in, 1 over 2 pi r in. That's this normalization factor here. 1 over 2 pi r on the outside. We do this integral. It will be 1 if k is equal to k prime. That's obvious. If k is equal to k prime, then this isn't here. This product is 1. And it's just the integral from 0 to 2 pi r divided by 2 pi r. That's 1. If k is not equal to k prime, then the integral is 0. Okay? The integral is 0 because basically what you're doing, these things are made out of sines and cosines, right? This one is made out of functions which oscillate like this. This one is made out of functions which oscillate with a different period. And the product will be positive some places and negative other places. Here the product is negative, here the product is positive. If we take two different values of k and look at it along the line, we'll find that it cancels as much as it adds. The result of that is that this integral is always 0 for k not equal to k prime. So there's an easy way to say it. This is just equal to a Kronecker delta, a thing which is 0 if k is not equal to k prime and 1 if k is equal to k prime. Now k itself is not quite an integer. K is related to an integer, and so what we'd actually write is that this is equal to delta of n and n prime, where n and n prime are the appropriate integers going with k and k prime. That's standard quantum mechanics raising its head for us. Orthonormal eigenfunctions being the eigenfunctions of a Hermitian operator. So that's good. All of that is good. Yes?
Is that a definition?
No, this is not a definition. This is a theorem.
Theorem.
Oh, yeah.
Okay.
Yeah. The value of integrals is never, well, the value of integrals as a general rule for well-defined functions is something you calculate.
Okay, but what I'm not clear with is where does that come from? Where do you, are you just trying to show that the two-way functions are orthogonal?
You're asking me, can I prove this?
No.
No.
I'm asking, where does it come from?
Because they are eigenvectors with different eigenvalues of a Hermitian operator, it implies that they're orthogonal.
Okay, and that shows that.
Yeah, this is a, either we can think of this as a consequence of the fact that they're eigenfunctions of a Hermitian operator, or we can say this is confirmation of the, of that fact. Yeah.
There's sines and cosines that are periodic over the same interval.
They're periodic over the same interval, but they don't have the same,
They have the same wavelength, they're going to integrate out to 0.
If they do have the same wavelength? If they don't, that's right. That's all. Yeah, that's all that's happening. Right. Right. For example, well, yes, that's right. If they don't have the same wavelength, they will cancel out as much as they add. Okay, so this is an example of the orthonormality, the orthonormal character of the eigenfunctions of a Hermitian operator. In other words, these functions, thought of as vectors, form a basis for the vector space. The next step, if we were trying to get to this continuum limit, we want to replace sums by integrals and Kronecker deltas by delta functions. I'm not going to go into that very much except to tell you that to do so, what we basically do is we multiply up each of these wave functions by a large number. In other words, instead of taking wave functions which are in the standard sense normalized to 1, we multiply them by a big number. How big a number? We simply multiply them by the square root of r. If we take each wave function of this type and multiply it by the square root of r, it's no longer a truly normalized wave function, but now we'll just define it. Psi p of x will, instead of being this thing, it'll be the same thing, e to the I px, over the square root of pi, square root of 2 pi, without the r here. That means these wave functions have been stretched out by a factor of r. Right? Stretched out by a factor of square root of r. Now that's not going to change the fact that if we take two different ones, where did I put it? If we take two different ones, that the integral will be 0. That's not going to be affected by multiplying by r. It'll be 0 if k is not equal to k prime. That will still be true. But what if k is equal to k prime? Originally, we had 0 there. Originally we had 1 there. If k is equal to k prime, we had 1. Now we're going to get something big. If we get rid of the if we stretch out the vectors by a factor of square root of r, then on the right-hand side, we will get r if k is equal to k prime. In other words, we now have that the inner product between these two functions as a function of, notice it is a function of k minus k prime. If I combine these exponentials together, it really just becomes k minus k prime x. It's a function of k minus k prime. It has the property it's 0 if k is not equal to k prime, but it has the property that it's very big, namely equal to r. We're imagining r getting very, very large now when k is equal to k prime. So we've stretched it out to make the inner product be a delta function instead of a Kronecker delta. Right? Once we do that, we can then rewrite, we can write the original equation, which I haven't written down, but I'll write it down now, that the inner product between two eigenvectors, instead of being equal to a Kronecker delta, becomes a delta function, delta of k minus k prime. So here was the step where we stretched out the vector and made a delta function out of a Kronecker delta. We multiplied each wave function by the square root of r. Notice that the wave functions still have the square root of 2 pi in them. All right. That is where that's where the Kronecker delta became equal to the delta function. Once we do that, we can freely pass to a notation where sums are replaced by integrals, where Kronecker deltas are replaced by delta functions, and just comfortably go ahead, more or less blindly, using delta functions. Now, I'm not going to say anything more about it than that right now. Yeah?
I'm not sure in that integral you have that shouldn't there be a square root of r somewhere?
No. Not anymore. It's r now. What we had, let's go back. What we had is if I put r down here, then it was equal to 1 if k is equal to k prime. I simply multiplied it through by the square root of r and another square root of r and got r here. In other words, an inner product which was 1 now becomes an inner product which is very large if k is not equal to k prime. That it happens to be a delta function, a legitimate delta function, is something that you can prove, but I simply wanted to show you where at what stage, at what point, the stretching of the vector took place. The stretching by the factor of square root of r. Okay, that's one important observation. Now, what I want to do is show you the connection between momentum states and position states, the momentum basis and the position basis. But before I do, I want to come to a very, very simple theorem which we've already studied, but get around it a little more. First of all, we've discussed the inner product of two vectors, a, b, and the inner product of two vectors is a number. There's another concept which is the outer product of two vectors, the outer product of two vectors, and it's written this way, BA. This is the inner product of the ket vector B with the bra vector A. This is the outer product of the ket vector B with the bra vector A. What the hell does this mean? This is no longer a number. This object is an operator. It's a linear operator, and the way that it works is if you take this object, think of it now as an object in its own right. Just in order to indicate that it's an object in its own right, let's put a red bracket around it. What you do with this object is you multiply it by vectors. In other words, you act on it with this being thought of as an operator. Let's operate on the vector c. What does this mean? All right. It means just about what the notation might lead you to believe it means. It means the inner product of A with C, the A, which is adjacent to the C over here, just write down the inner product of A with C. That's a number. That is a number times the vector B. So the result is a vector. This is an operation on vectors which give vectors times numbers. Vectors times numbers are vectors. The outer product of B with A is legitimately a linear operator. Cool? It's a dyad. It's called a dyad, and that's what it is. Okay, that's one observation, important observation. Now, another observation is the following. If I have a basis of vectors, I can expand any vector in it. I can write that this is a sum of coefficients v sub n. No, I'm sorry, I did not mean to write this. I want to write v as a vector is a sum of a set of coefficients times the nth basis vector. That's what a basis is good for. It's good for writing any vector as a sum of the basis vectors. What are these coefficients v sub n? The coefficients v sub n are equal to the inner products of v with the basis vector n. The coefficients themselves are nothing but the inner product of the vector that you're expanding with the basis vectors themselves. This is easy to prove. I think I actually proved it in class at one point. So you can rewrite this as the sum of, now let's do it right, let's put first n. That's this n over here. And then let's put v sub n, which is n times v. You can read this in two ways. Both of them are correct. The sum is, of course, sum over n, all basis vectors. Two ways that you can read this. You can say, first of all, that this is just a sum of vectors with coefficients. The coefficients being these v sub n's. But the other way that you can read it, which is also correct, is to say that we have a set of a set of operators, these kind of outer product operators, one for each basis vector. You add, what happens when you add operators? You get operators. So you can read this another way. You can read this as saying that there's a certain operator. Let's write it out. A certain operator, I'm going to call it I, and it's equal to the sum over n of the dyads nn. That's what appears here. And it has the property that if you multiply it by any vector v, you get v. I times v is equal to v. This operator, which is composed out of the basis of dyads, is nothing but the identity operator. The identity operator means the operator which, when it hits any vector, gives back the same vector. Call it the unit operator. You can call it just plain 1. You can call it I. You can call it a number of different things. But whatever it is, it's something that when you see it, it just gives back the same vector to begin with. That's a useful formula. Let's write it out over here, that the identity operator, the thing which does nothing when it hits a vector, just gives back the same vector, is the sum over a basis of dyads. An example of this would be to take momentum eigenvectors. But if the momenta form a continuum, if we go to this limit where the circle is very, very big, and when we replace sums by integrals and Kronecker deltas by delta functions, this becomes I is equal to the integral over k of k with k. At some point, I'm almost certain I'm going to lapse into calling kp and call it the momentum. That's just setting h bar equal to 1. So if I do that, either yell out or just swallow it and say he set h bar equal to 1 again. Yeah?
On that formula, I equals the sum to n, would it be right to say that you could say that would be, instead of calling it n as the sub, call it I, and ni, and I, basically? I'm kind of confused by that notation, because you've got two n's in there.
Yeah, it's the,
Three n's in there, basically.
well, this sum just says sum over them. That's just a summation index.
It's just all the vectors in that space.
Yes.
Okay.
You sum over all the basis vectors. All the basis vectors, yeah. All right, now, there may be many bases, many possible bases. Many possible bases. A basis is just a set of orthonormal vectors. There may be more than one. For example, just an ordinary two-dimensional space, a real two-dimensional space, that's a basis, that's a basis. That's a basis, those vectors. It's the same for any one of them.
It's common with an uncountable basis to just use a letter like alpha, both as the index and the way you're using n there.
For an uncountable basis.
Yeah, you just write alpha as the sum over alpha, even though you can't really sum over it. But
It's common to do so, but in practice, what it means if the basis vectors are labeled by a continuous variable is it means integral. All right? It means integral. So in practice, to make it concrete, one would replace the sum by an integral. And remember, wherever there are inner products between basis vectors, they're not Kronecker deltas, they're delta functions. All right? They're delta functions. All right, this is a useful fact. And it is, in fact, at the heart of Fourier's theorem about Fourier transforms. So let's discuss Fourier's theorem and its relationship with quantum mechanics, state vectors describing particles with definite positions, state vectors describing particles with definite momenta, and their various wave functions. Let's see. I have too many things in front of me here. Ah, here it is. Okay. Definition. If psi is a state of a particle on a line, then and x is an eigenfunction of position with eigenvalue given by the label here, then the wave function is by definition the inner product of the state vector with the eigenvector of position. This is called psi of x. According to the postulates of quantum mechanics, the product of this with its complex conjugate, psi star psi, is the probability to find the particle at x, or the probability density to be precise. Okay? Now, let's apply this in particular to a wave function of definite momentum. Let's call it p. If I call it p, I'm going to have to put an h bar in. Let's call it k. This is a definite state vector describing a particle with momentum k, and I'm interested in its inner product with a particle of position x. It's the wave function of the particle with momentum k. It's the wave function of that state. All right? What is that? That is just e to the I kx over the square root of 2 pi. I've left out the r in here because I'm going to use delta functions instead of Kronecker deltas. All right? All I've done here is to use the wave function that we've written down up here, thrown away the square root of r in the denominator, and written that that wave function, psi of x, is just e to the I kx. So what I've discovered is that the inner product of a momentum wave function, a momentum state, with a position state, has this nice symmetric form. Notice it's sort of symmetric between k and x, e to the I kx over the square root of 2 pi. That's one observation. Now let's take a more general state, psi, and I'm interested in what's the probability that it has different momentum. Here is the probability amplitude for it to have different positions. I multiply it by its complex conjugate to find the probability. Now I want to know what's the probability for finding different momenta if I were to measure the momentum instead of the position. Well, that's related or is equal to the square of this quantity. K, of course, being related to the momentum by a factor of h bar, which I will ignore. The inner product of psi with k, quantity squared, multiply this by its conjugate. Call this here, let's call it psi twiddle of k. It's the thing that you square to find the probability for different momenta. I put the twiddle up here to indicate that it's not just psi of x, it's a wave function that depends on momentum, not on position. Its square is the probability that the particle has different momenta, if I were to measure the momentum instead of the position. Okay, let's calculate that. Let's calculate that by using our trick. Where is our trick? Our trick is over here. This is the trick we'll use. What we're allowed to do is we're allowed to substitute, or not to substitute, but insert into any expression. Let's see, which one do I want to put in there? Excuse me 1 minute. Yeah. X psi integral dx. What I've done here, this is not quite what I've used. What I've used is I is also equal to the integral dx of xx. Both of these are bases, the k basis and the x basis, the momentum basis and the position basis. The position vectors are all orthonormal, or at least they're normalized with a delta function, just like these k vectors here. And so what I've done in here is to insert unity in the form of the sum of dyads, summing over a basis. Okay? Well, what is this object over here? This is psi of x. What is this object? This is e to the I kx. Let's see, it's actually a complex conjugate of this. Notice over here I have k on the right and x on the left. Here I have k on the left, x on the right. What's the relation between this and this? Complex conjugate. So I actually have to put e to the minus I kx, all divided by the square root of 2 pi. 1 over square root of 2 pi, integral e to the I kx psi of x dx. That's equal to what? That's equal to psi twiddle of k. What's the bottom line? The bottom line is if I want to know the probability for a given momentum, I take the wave function as a function of position, I multiply it by e to the minus I kx, and I integrate. That gives me a function of k, and that function of k is the thing that you square to find the probability for different momentum. Okay? So that's the mathematical logic connecting position and momenta. This operation has a name. Taking psi of x and multiplying it by e to the minus I kx and integrating dx is called the Fourier transform. So this is the Fourier transform, the momentum space wave function, psi twiddle of k, is the Fourier transform of the position space wave function. Okay. You can go in the other direction. You can do exactly the same thing to relate the position space wave function to the momentum space wave function. You go through exactly the same operation, or almost exactly the same operation. Let's see if we can do it. Let's see. What we write is that psi of x, I'm taking this pattern that we have here, but interchanging x and k. So psi of x is by definition x times psi. That's its definition. And now to calculate it, I'll insert a complete set of momentum states. X, k, k, psi, integral dk. Again, I have now done exactly the same thing, except I've expressed the identity operator I as an integral over k. Well, what's this? This is nothing but psi twiddle of k. This is psi twiddle of k. And what is this? Where is it? Here it is right over here. It's e to the I kx integral dk. Square root of 2 pi, right? That's psi of x. So look, we have a reciprocal relationship between psi of k and psi of x. On the one hand, psi twiddle of k is gotten by integrating over x of psi of x with e to the minus I kx. On the other hand, psi of x is gotten by integrating over k of psi twiddle of k. Let's put the two formulas down next to each other and compare them. Here. Psi twiddle of k is equal to the integral of e to the minus I kx over square root of 2 pi times psi of x. If somebody tells you the position space wave function, you can immediately read off the momentum space wave function, okay, from this formula. On the other hand, if somebody tells you the momentum space wave function, you can read off the position space wave function, e to the plus I kx over the square root of 2 pi psi twiddle of k. The only asymmetry here is that one of them has an e to the minus I kx and the other has an e to the plus I kx. So this little formula here, this type of formula here, is rather powerful. And it encapsulates, among other things, the reciprocal relationship of Fourier transforms. That
K have negative values too?
can what have negative values?
K.
Absolutely. Absolutely. Momentum can be negative. Just means the particle's going in the negative direction.
Is there a physical interpretation of that symmetry between x and k?
Well, is there a physical interpretation? It was not obvious from classical mechanics that there should be any reciprocal relationship between momentum and position, at least not until you get to the Poisson bracket formulas, where you begin to see that they are symmetrically related to each other. This is all very, very closely related to that story of Poisson brackets, but we're not there yet. But this is another example of the reciprocal relationship of momenta and position. Okay, good. Here's something you can sort of guess. In other words, there are two representations of the same thing. The representation, we have a state psi. We can represent that state psi in terms of a wave function psi of x, whose square is the probability. When I use the word square, I mean times its complex conjugate, whose square is the probability for different positions. Okay? But we can also use a psi twiddle of k, which has the same information. How do I know it has the same information? Because you can go back and forth between them. One simple vector is described in two distinct ways, one in terms of a wave function of position and the other in terms of a wave function of momentum. Now, let me remind you now, how does the position operator act on psi of x? What does it do? Multiplies by x. This is an operator now, it's not just coordinate x. It multiplies by x into psi of x. Okay. How about the momentum operator, k? Thought of as an operator, what does it do to psi of x? Minus I d by dx of psi of x. Now this reciprocal relationship, which I'm not going to prove, but it's more or less clear from the symmetry pattern between x and momentum here, is first of all, how do you think the momentum operator acts on psi twiddle of k? Well, psi twiddle of k, what does it do? Multiplies by k. K times psi twiddle of k. So if we happen to have had the wave function in the momentum basis, called the momentum representation, if we had the state vector expressed in the momentum representation and we wanted to know how k acts, it's easy, we multiply by k. How about x? How does x act when it acts on the wave function psi twiddle of k? What would you guess? Plus or minus? Plus. Plus. It's this funny asymmetry between plus and minus in the Fourier transform formula. It is plus I d psi twiddle by dk. All right, these are, first of all, formulas about Fourier transforms, first of all, among other things. But there are also formulas about quantum mechanics. These formulas, of course, were well known before quantum mechanics was ever invented by people who did Fourier analysis. So they were just reinvented by quantum mechanics for the purpose of studying particles on a line, for example. Yeah.
Yeah, so you can't represent the state vector with both of them. It can only be one or the other.
Yes, that's right. The question was, you don't represent the state, either one or the other. Let's say either one or the other. You represent the state vector as a psi of x or a psi twiddle of k, and most certainly not a function of k and x.
Is that because of the Heisenberg uncertainty?
Right. Or you could say it the other way. The Heisenberg uncertainty relation is the fact that the function of x is, well, this reciprocal relationship. No vector is both an eigenvector of k and an eigenvector of x. All right, so there is no state which has a definite position and a definite momentum. And in fact, it's as bad as it could be. A state of definite momentum has a completely uncertain position. And by symmetry, by now you can see there's a symmetry between the two problems. So if a state of definite momentum is smeared all over the place in position, then a state of definite position has a completely uncertain momentum. That's the character of the position versus, or the position momentum correspondence, if you like.
Can you remind me what the physical interpretation of conservation of phase space volume would be other than just to restate it?
I can remind you, the conservation of phase space volume will become the unitarity of operator, of the time development operator.
Well, just within classical mechanics, but, I mean, like, I guess.
Within classical mechanics, the conservation of the phase space volume is the conservation of the phase space
Right,
volume.
it doesn't have an interpretation physically, other than just a consequence of when you do a transformation, you get.
Well, you can kind of think of it as as a classical version of the statement that distinctions between states are maintained with time, that the phase space volume doesn't shrink. For example, if you start with a phase space volume which looks like this in phase space, which has many, many points in it, it will not evolve to a single point, for example. All right? If it did evolve from a single point, that would mean that there was no way to figure out where you came from. So the conservation of phase space volume is, roughly speaking, the statement that distinctions between different states are maintained, and there's a more quantitative version of it, which is just conservation of phase space volume. In quantum mechanics, it becomes the unitarity of the, which we haven't gotten to yet. We may or may not get to it tonight, what unitarity means. But unitary is the quantum mechanical analog of, what do you call those transformations in classical mechanics? Canonical. Right. Which preserve phase space volume. Okay.
The derivatives, I'm sorry, there with the K operator times the psi of x. I'm sorry, how did you get that?
Here?
The seventh.
This one?
Yeah, or that one too.
Well, I just guessed it from this.
Yeah, and I'm sorry, how'd you get that one?
Oh, that was the original starting point for what momentum is.
Okay.
Momentum was the object represented by the linear operator minus I d by dx. Remember, we proved that minus I d by dx was Hermitian. Right? Minus I d by dx equals k hat times psi of x. That's the statement that, well, thought of as an operator equation, it's the definition of k hat. If we actually put a definite k here and said that this was psi sub k, this would be the eigenvalue equation that says that the momentum operator acting on psi of k gives us k times, gives us the eigenvalue times psi. But let's just leave it this way for the moment. All right. So I went, yeah. I may have just confused you and I didn't mean to. I just guessed this one from this one. But I also know that it's true. And it's easy to work out, quite easy to work out from all the definitions. Yes, sir.
When we did that, I seem to remember you putting some weasel words in there.
Some which?
Weasel words?
Weasel words? Weasel words. That's a weasel word.
That may or may not have anything to do with what we thought, or what we think it was momentum, but that's what we'll call it.
No, the point is, thus far, we haven't established a clear connection between what we're quantum mechanically calling momentum and what we classically call momentum. Okay? Let me tell you right now what that connection is. All right? Without deriving it, let me tell you what it is. There are wave functions for a problem involving a particle moving in a potential well or something like that. There are wave functions which hold themselves together pretty well. As long as the potential is smooth and not too crazy, then the motion of a wave packet. What is a wave packet? I'll tell you what a wave packet means. It first of all means that the wave function psi of x is concentrated in some region with a nice smooth shape, perhaps a shape that looks like a bell curve, but it doesn't have to be exactly a bell curve. So psi of x looks like this. But it also says that the momentum space wave function is also, that's psi of x, but here I'm just writing the magnitude of it. I haven't tried to express the phase of it, just the magnitude of it. It is, of course, a complex thing, and I haven't tried to indicate how the complex part of it varies across here, the magnitude of it varies like this. All right? It's also implicit in the notion of a nice wave packet that psi of k, can that be seen? Psi of k, psi twiddle of k, is also a nice concentrated wave function of some sort.
You mean those to be Gaussian?
Gaussian would be an example, but it doesn't have to be literally a Gaussian. A Gaussian is a good example, but it does not have to be literally a Gaussian. Right? Just a wave function which is concentrated at some position and concentrated at some k, but not infinitely narrow in x, because if it's infinitely narrow in x, it will be spread all over the place in k, and vice versa. All right, now, if it is concentrated in k, that means it looks more or less like a plane wave, like an e to the I kx, right? Right. So that must mean that it looks like this, or that the real and imaginary part of it looks something like that. It oscillates, the real and imaginary part of it oscillate almost as though it were a momentum wave function, but with an envelope that's fairly concentrated in x. Wave functions which look like this. For example, you just take e to the I kx and multiply it by some function of x which looks like that. This will be something which is concentrated in x by virtue of this factor, but it will also oscillate pretty much like a plane wave inside that lump. Those are wave functions that describe particles not with very precise momentum and position, but with fairly precise momentum and position. Somewhat precise momentum, not in violation of the uncertainty principle, but more or less saturating the uncertainty principle, meaning to say as certain as possible in both position and momentum. Now, those wave functions will move, they will propagate. The Schrödinger equation, which is the equation which tells you how these change with time, will have these wave packets moving. And they will move more or less, or similar, to the motion of a classical particle. That's the theorem that will prove. The theorem that will prove, when we finally get to it, is that the center of the wave packet in position moves very much like the position of a classical particle. In fact, as long as the wave function maintains its shape like this, it moves along like a classical particle. And with time, first of all, the position will change with time, but also the momentum will change with time. That means that, for example, if the momentum increases, that might mean that the wave packet gets more and more oscillating, or less and less oscillating. Both the momentum and the position will change. The wave packet, if it's a nice problem, will maintain its integrity and move with both a position moving in space and a k moving in momentum space. The theorem that will eventually prove is that the centers of these wave packets move like classical particles, and the center of their momentum distribution move with the same equation of motion that the classical momentum evolves with. That's the bridge to classical physics, the motion of wave packets, but we're not there yet. So for now, we just call these things position and momentum, and accept on faith that there's some connection between classical momentum, classical position, and quantum mechanical momentum and position. Okay. Let's take a 5-minute break.
Clarify, A and B, you said the inner product of A and B is a number. If A and B are complex vectors, that can be a complex number, correct?
Where are we? Up here?
Very simple, yeah.
Yeah.
So if A and B are complex vectors, the inner product can be a complex number.
In general, yes.
So I'm trying to get my head around what is the outer product of complex vectors.
A non-Hermitian operator in general. Now, we haven't discussed, yes, we have discussed.
Once you multiply it over there and you got AC, and it's a ket.
Rich. Yeah, but you can ask, what's the connection?
Operator times ket equals ket.
Operator times ket equals ket, yes. But the question is, in what sense is this complex? Okay, in what sense is this complex? Well, it's complex in the sense that it's not equal to A times B. These are kind of complex conjugates of each other, but strictly speaking, the correct term, which I haven't introduced yet, is they're Hermitian conjugates of each other. We've discussed what a Hermitian operator is, but we have not discussed what the Hermitian conjugate of an operator is. And we will eventually, but if you happen to know what it means, this operator and this operator are Hermitian conjugates of each other, which is the operator version of complex conjugate. Any other question before we take a break? Okay. The thing that we have seen rather clearly is the notion of incompatible observables, incompatible operators that don't have the same eigenfunctions and therefore cannot be definite in the same state. We're starting to get some idea about how the logic of quantum mechanics works, and that it works quite differently than the logic of classical mechanics. In classical mechanics, you would simply specify a position and a momentum. In quantum mechanics, you can specify a position or a momentum, or you can specify a more complicated object, a wave function psi of x, which contains probability information, or you can specify the same state vector in terms of a momentum space wave function, which has information in it about the momentum. But not both. But not both. Not both at the same time. It's one or the other. I like to say that, that quantum mechanics often replaces the word and by the word or. Classical physics, you might say that a particle has a position and a momentum. In quantum mechanics, you would say a particle has a position or a momentum. You work in one representation or the other, and at no point do you ever assign a notion of probability to more than one variable if those variables are incompatible. We'll come to examples of compatible variables, but the particle on a line is not a good example for that. Now I want to come to a system which is in many ways much, much simpler. It's a system which has only two orthogonal states. Now, the last time I taught this course, I did this exercise by using the spin of an electron. The spin of an electron is like a heads or tails coin, which if you measure it along some axis is either up or down, and it's never in between. On the other hand, you can measure it along any axis, so it gets a little complicated. This time, I want to do a different system, which also has two orthogonal states. You can think of it as the spin of a photon, if you like, or better yet, the polarization of a photon. Light is polarized, or light can be polarized. Light is made of photons, first of all, so think of light as particles now. And we're interested in the quantum mechanics of those particles. But don't completely forget the fact that there's also a wave theory of light. Okay? They've got to be made compatible somehow. Let's just go to the wave theory of light for a minute. There's a notion of the polarization of light. Light is an electromagnetic wave, of course, and a typical wave describing a light wave moving down this axis, let's say with a certain wavelength, would be a wave consisting of the electric field, and in this case the electric field oscillates in the vertical plane here, positive to negative and so forth, but it also has a magnetic field, and the magnetic field is always perpendicular to the electric field. And so an ordinary electromagnetic wave, let's try to draw it. This would be the electric field, and there would be the magnetic field in the, let's see if we can draw it. Electric field oscillates in the vertical plane, and magnetic field oscillates in the horizontal plane, like that. Of course, you can rotate it. They're not out of phase. They're in phase. I just drew. No, the reason this is lagging behind here is because I projected it onto the x-axis. Is that drawing clear? No. Sorry, too many people are talking. I can't hear. That's what I'm afraid, yeah. Yeah, okay.
The picture is clear. My question was, should they be out of phase?
No,
No, okay,
no.
good.
No. Now this is a plane polarized plane polarized light wave, meaning that the electric field oscillates in a plane. Right? Oscillates in a plane. If this is called the z-axis, and the other two axes are x and y, and supposing I look at that wave looking down along the axis, we have an x and a y-axis. And in this case, the electric field is along one of the directions. That electric field and the magnetic field perpendicular to it. The definition of the polarization of a light wave is the direction of the electric field. However, we don't distinguish whether the electric field is up from whether it's down. In other words, we just say, for example, it's polarized in the y direction. It's an oscillation up and down in the y direction, but just think of it as a wave polarized along the y-axis. Or the wave can be polarized along the x-axis, or it can be polarized along any axis. The definition of the polarization is the plane or the direction of the electric field oscillations. That's arbitrary. You could have defined it to be the magnetic field oscillations, but that's how it's defined. Now, if you take a long wavelength electromagnetic field, radio waves or microwaves, radio waves, let's say, and you run them past a grid consisting of wires in the vertical axis here, the wave will come out on the other side polarized. It will come out polarized along a particular axis. Let's see, does it get polarized along the axis of the wires, or does it get polarized along the direction perpendicular to the wires? Do you know? Perpendicular to the wires. Perpendicular to the wires.
Wires short the E field out. The wires short out the E field.
Exactly. The wires short out the E field in the vertical direction, but they allow the E field in the horizontal direction to go through. Right? There's no current flowing in the horizontal direction. All right, here's the way to say it. Okay, here's the way to say it. Supposing you just took a square of conducting material and you shined light on it. What happens to it? It reflects. Doesn't go through it at all. Okay? Now, supposing we take this grid of wires. How does it reflect? What causes it to reflect? What causes it to reflect is currents that are generated in the piece of metal here. For example, an electric field comes in here, starts, charge is moving, the charge is moving, make a reflected wave, and the wave reflects off because it starts, because the original wave starts some current oscillating in the metallic conductor. Now, here, the only direction that the electric field can drive current is in the vertical direction. It's not possible to drive current in the horizontal direction because there are no wires in the horizontal direction. The result is that a vertically polarized electric field, a wave coming in with vertically polarized electric field, will start a current going and will get reflected. A wave with its electric field in this direction, it just behaves exactly as if there was no grid there. It cannot start any currents going, and so it just goes right through. So the field that goes through to the other side is perpendicular to the direction of the grid. A grid like this is a polarizer. At a microscopic level, roughly speaking, a polarizer is just a grid of lines like this, which transmits through it one direction of polarization and either reflects or absorbs the other direction. Sometimes it just absorbs the other direction. Sometimes it transmits it through. So that's what a polarizer is. Whatever wave falls on it, only the component along the direction of the axis of the polarizer gets transmitted. Okay, the direction of the polarizer happens to be perpendicular to the direction of the current flow, but nevertheless we speak about the axis of the polarizer as the direction of transmission of the electromagnetic wave. Now, electromagnetic waves are made out of photons. Okay. If we take a polarizer, let's draw the polarizer this way. This means that it transmits vertical polarization. And we send just a single photon through there. The single photon may or may not pass through. If it happens to be a photon which is associated with an electromagnetic wave with vertical polarization, it will pass right through, come out the other side, and what's more, it'll come out the other side with the same polarization that it started with. On the other hand, if it's a photon which happens to have been associated with a horizontal polarization, then it won't go through. It may get absorbed or it may get reflected, but in that case, nothing comes out.
Does the reflected photon polarize?
The reflected photon may be polarized, yes. It'll be polarized. But I want to ignore the reflected photon. It's not hard to imagine a polarizer which actually absorbs the other polarization. I want to just ignore the one which is reflected or just let it be just dropped from the picture. If it goes through, I count it as a photon which has successfully passed through the polarizer. If it gets bounced back, it's for my purposes lost. Now, this is a device for preparing the particular state of polarization, which we can call vertical polarization. There are two states of possible polarization. Now, you're going to ask me, what about polarizations at different angles? We'll get to it in a moment. But any given photon, no matter what the direction of polarization of the light wave that carried it, in other words, no matter how that photon is prepared, it will either get transmitted or reflected. Right? Either one or the other. Even if that photon were polarized, even if the original electric wave were polarized along some other axis, for example, supposing the electric field of the classical wave describing that photon happened to look like this. We let through photon by photon, one photon at a time, and we ask what happens to a photon. You might think that a fraction of the photon goes through and a fraction of the photon gets reflected. A fraction of the energy of the photon goes through and a fraction of the energy of the photon gets reflected. But no, photons are indivisible. You can't break them up like that. What happens is the photon either goes through or it's reflected. It may have a probability for going through and getting reflected, but it will do one or the other, discrete choice, nothing in between. So there are only two possibilities. The photon makes it through, in which case it's called vertically polarized when it gets out here, or it doesn't get through, in which case it must have been horizontally polarized. Now, next fact, there's a kind of consistency. If you manufacture a vertically polarized photon this way, by sending it through the vertical polarizer, and it happens to come out, then it is definitely vertically polarized. You can send it through another vertical polarizer, and it will, with probability 1, go through. Okay? So you can think then of the polarizer as both a measuring apparatus and a preparer of states. It prepares states. In this case, this polarizer prepared a vertical polarization, but you can also use it to detect what the polarization is. For example, having made it vertical here, if I send it through the next polarizer, if the next polarizer is vertical, it will definitely get through, confirming the fact that it was vertically polarized. If, on the other hand, I happened to prepare the photon with a horizontal polarization just by rotating the polarizer so that it comes out this way, then it just gets blocked by this polarizer. So this polarizer can be thought of as an apparatus which is measuring the direction of polarization of the photon. If it makes it through this polarizer, then it has detected a vertical polarized photon. If it doesn't make it through here, it has detected a horizontally polarized photon. Okay? We can prepare photons by sending them through polarizers, and we can detect their polarization by checking what happens at the next polarizer. So the same apparatus can be thought of as an apparatus for preparing a state and measuring a property of the system. And as I said, if we restrict ourselves to an apparatus here which measures polarization, what's this doing? This is measuring polarization in the XY plane. It's either vertical or it's horizontal, and this apparatus tells us whether it's vertical or horizontal. All right. Let's start doing some quantum mechanics. Let's try to make quantum mechanics out of this. In other words, let's try using the formalism that we've concocted to describe the polarization of the photon. We're not going to worry about the position of the photon. We're going to take the polarization itself as a system and not worry that much about where the photon is, All right, there are two orthogonal states of polarization. The two orthogonal states of polarization we could label, first of all, with a ket vector. And we could label them this way. This represents polarization along the x-axis. We could also just call it polarization along the x-axis. And we could, if we like, associate with it a column vector. The column vector could be taken to be 1, 0. This represents the vector polarized along the x-axis, represented by a column vector with a 1 here and a 0 here. The 1 indicates that it has probability amplitude 1 for being along the x-axis and 0 probability for being polarized along the other axis. These are three different notations I could use to describe the same thing. Then I have, of course, the other possibility that the photon is polarized in the other direction. We could call that a photon polarized along the y-axis, or we could call it the column vector 0, 1. X and y are distinguishable, distinct, measurably different states of being of the photon. They are completely distinct. If I create a photon like this and I send it through the next polarizer, if the polarization is horizontal, it will definitely go through. If I create a photon like this, it will definitely not go through. So these are two completely distinguishable. A single experiment can tell you which of these two states a photon is in. And therefore, these must be orthogonal vectors. X and y must correspond to orthogonal states. That, of course, is consistent with this notation here. Remember how we calculate the inner product between the two vectors? We multiply the first component times the complex conjugate of the first component of the other one, and so forth. These are two orthogonal vectors. So we can regard these as basis vectors in a two-dimensional space, the two dimensions corresponding to the two mutually exclusive directions of polarization. So this is equal to 0. They're orthogonal. On the other hand, we can also choose the vectors describing the two configurations to be normalized. We can choose them to be of unit length. In other words, we just invent or concoct a vector space, a two-dimensional vector space with mutually perpendicular directions, x and y, and unit vectors along those directions to describe the two possibilities. This is what quantum mechanics would tell us to do, and these are then a basis vector. These are then a pair of basis vectors in a two-dimensional vector space. This is a very simple system, much simpler than the particle on a line. That's, of course, because we're ignoring the motion of the photon. We're just dealing with the polarization of it. Just two possibilities. Yeah.
Is this thing to do with observables? Before we talk about observables.
Yeah, we haven't, yeah, we're just about to do that now.
Okay, so the question is you said that these states represent the polarization one way or another. So is that an observable?
You can certainly observe it. The question was, is the polarization an observable? You can observe it. You can send the photon through a vertical polarizer, and it will either go through or not go through, and that will select out for you whether the photon was vertically polarized or horizontally polarized. So yes, it is an observable.
Okay, well, I thought we talked about states not being observables.
No, the states are not observables. The things you observe are the polarization, whether it is or isn't horizontal. The states represent the possible configurations of the photon. The observable is the polarization. Now we're going to talk about the observable that corresponds to the polarization. Let's define an observable quantity by the following rule, that if the photon is horizontally polarized, we're going to write this funny P here, represents polarization, and it's going to represent an operator. It's our operator which will represent the polarization of the photon. And it has the property, by definition, that if the polarization is horizontal, then P is equal to +1, and if the polarization is vertical, it's equal to -1. That's a definition now. I will simply assign the number +1 to horizontal polarization and -1 to vertical polarization. That's the thing which becomes the observable. It's either +1 or -1. It has a numerical value. If the photon goes through the polarizer, I assign +1. If it doesn't go through the polarizer, depending on the direction of polarization. But we'll define now a polarization. This is the polarization operator for polarization in the xy plane. I'm going to put a symbol there which is intended to show the xy axes. This is the polarization in the xy plane, right? And it's equal to +1 for horizontal polarization, -1 for vertical polarization. That's a definition. If we have a bunch of photons going through, and we see one go through, let's assume the polarizer is oriented along the horizontal direction. Polarizer along the horizontal direction. We send a bunch of photons through. If a particular photon gets through, we put it on notebook plus. If a photon gets absorbed or reflected, we put it on notebook minus. And that way, we define a numerical quantity which we can call the polarization. But it's the polarization in the xy plane. That's polarization in the xy plane. And here's the way we define it as an operator. When it operates on a polarization along the x-axis, what does it give? +1 times x. In other words, x is an eigenvector of this polarization operator with eigenvalue +1. What about polarization along the y-axis? Same operator, acting on a different vector, y. Y has eigenvalue -1, and so this is equal to -y. That completely specifies the operator P with this subscript xy polarization. You know how it acts on x, you know how it acts on y. In fact, you know how it acts on any linear superposition of x and y. You can even represent it as a matrix. Let's represent it as a matrix. If we represent the vector space as column vectors, we can represent the polarization as a matrix. Here's the matrix. Here's the matrix representation of it. It's very simple. It's just the matrix 1, -1, 0, 0. Let's check it. The x polarization is represented by 1, 0. What does this give? 1 times 1 plus 0 times 0. 1, 0 times 1, 1 times 0, 0. So that says that this polarization operator acting on the x polarization gives back the x polarization. That's just this equation. And let's try the other one. 1, 0, 0, 1, minus 1, 0, 1. 1 times 0 is 0. 0 times 1 is 1, 0. 0. 0 times 0 is 0. Minus 1 times 1 is minus 1. And that's equal to minus the original vector, 0, 1. So in fact, this polarization operator, this operator here, or this matrix, represents as a matrix representation of exactly this operator. When it hits the x polarization vector, it gives it back. When it hits the y polarization vector, it gives minus the same thing. So this object, capital P, with a hat on top of it, is the observable. X's are the eigenvectors, which are states of definite polarization. All right. The vectors here, the two basis vectors, are states of definite polarization, and the observable polarization, the mathematical observable, is represented by the operator P. Any questions? Okay. So that's simple. But now you say, wait a minute, what happens if I orient my polarizer in another direction? Nothing's to prevent me from taking my polarizer and orienting it, for example, along the 45-degree axes. There's a, here's a polarizer. This is intended to be a piece of polarizer, but the polarizer is oriented along the 45-degree axis. Again, we can send a photon through it. What comes out the other end will be a photon polarized along the 45-degree axis. Obviously, this must be a different state than either one of these. Okay. But here's the kind of question you could ask. Let's draw it a little better. Here we have the photon, the polarizer along the 45-degree axis like that. Well, it can't be both. It can only be one of them. Oriented along the diagonal direction like that. And here's another polarizer here. I'm using the first polarizer to prepare the photon. So the photon goes through, comes out the other side. Which way is it polarized? Well, it's polarized the way the polarizer told it to be polarized, along the same direction as the polarizer over here. What happens if the second polarizer is along the same axis? What happens to the photon? It goes through. What happens if the polarizer is oriented this way? It either bounces back or gets absorbed. But what happens if the polarizer is polarized along one of the original directions? Not this, let's take it to be along the x-axis. This is the x-axis. What happens if the second polarizer is along the x-axis rather than the 45-degree axis? Then what happens is the photon either gets reflected or absorbed, nothing in between. The point is, even though somehow this polarization is halfway between the two possibilities here, the photon has no choice. It has no choices which are halfway between being reflected and being transmitted. It either gets reflected or transmitted with a probability, right? With some probability. The question now is, what state, and what would you guess the probabilities to be if this were at 45 degrees? A half and half. It's pretty obvious. It's got to be a half and half. All right. So let's now take, let's see how I represented this. I had some notation for this. Here it is. Yeah. All right. So let's take the photon which has gone through the 45-degree polarizer. The polarizer now is this direction here. The photon goes through it. and it comes out the other side with some definite state. That state is neither x nor y, but has an equal probability for both of them. Here's a guess, and it turns out to be the right guess. I mean, what's right and what's wrong is determined by experiment. So you do lots of experiments on photons, and you find out that the pattern that I'm describing is the correct pattern. But what would you expect it to be? Anybody want to make a guess what it would be? It's not x, it's not y. On the other hand, x and y are a complete basis. There's nothing that can't be written in terms of x and y. X plus y seems a reasonable possibility. The sum of the two vectors has equal amplitude in both directions, or equal coefficient in both directions. It's not quite right because it's not normalized. So we throw 1 over square root of 2 in front of it. Now it's normalized. The sums of the squares of the coefficients add up to 1. 1 over square root of 2 squared plus 1 over 2 square root of 2 squared is 1. This vector, whatever it is, has equal probability that when we send it through the next polarizer, which happens to be oriented along the x-axis, it has probability 1/2 going through. If we send it through the polarizer along the y-axis, it also has probability 1/2 going through. Right? So this is a superposition of the two original states with equal coefficients. That's my guess. If you like, that's a guess for the photon which is polarized halfway in between. We can also write it another way. Let's see, this is photon polarized along the 45 axis is this, which we can also represent. I'm using an equal sign, but I should be using a sign that says it can be represented by a column vector, and the column vector would be 1 over root 2, 1 over root 2. Now, these vectors are not, oh, this is one vector. Now, there's a second polarization. The second polarization is orthogonal to this and is in this direction. What happens if I send this polarization through this polarizer? Supposing I create a photon with this polarization in the minus 45 degree direction, and I send it through the polarizer in the plus 45 degree direction. Right. So we would expect then that the state vector describing polarization along the minus 45 degree axis would be orthogonal to the state vector of a photon along the plus 45 degree axis. Right. So let's see if we can find a vector which is orthogonal to this vector. Well, it's not very hard to find a vector which is orthogonal to this vector. It's just x over square root of 2 minus y over square root of 2, represented by 1 over square root of 2 minus 1 over square root of 2. Let's check that these are orthogonal. First of all, they're both normalized. Both of them, the sums of the squares of the coefficients add up to 1. No question of that. Are they orthogonal to each other? Yes. To check whether they're orthogonal, you take this times the complex conjugate of this. Everything's real here, so I can ignore the word complex conjugate. This times this plus this times this. All right, that's 1/2 minus 1/2. The inner product between them is 0. So they're normalized. They're orthogonal to each other. These two vectors are also a basis. This basis is just as good and has just as much rights as the original basis. It's just describing polarizations in catty-cornered directions. Okay. What is the probability that if I create this polarization and then send it through the vertical polarizer, the y polarization, what's the probability that it goes through? Well, of course, the answer is a half, but let's do it by using the rules of quantum mechanics. I want to know the probability that if I start with 45 polarization like that, 45-degree polarization like that, and then I send it through the vertical polarizer, the Y polarizer, this is the Y polarizer, that it goes through to the other side. In other words, what's the probability that this has Y polarization, that it has Y polarization? The answer, as always, is take the inner product of the vector describing the photon with the configuration that you're testing for. What would that be? That would be Y. And then take the square of that. That's the probability that this cattywampus polarization over here is polarized along the Y direction. The inner product of this with this squared. What is it? Well, it's easy to figure out. Let's just do it mechanically. This guy over here is x over square root of 2 plus y over square root of 2. That's this one. And this one over here is just y. Well, the inner product of y with x is 0. The inner product of y with y is 1. So the answer is 1 over the square root of 2. That's the thing before you square it. This is the amplitude. The amplitude gets squared to find the probability. So the probability is the square of this, which is just square of this, which is 1/2. All right, now I'm telling you something which is completely obvious, that the probability is a half, but I'm showing you how the formalism of quantum mechanics carries out that intuition. What about the probability that it's polarized along the x-axis? You do exactly the same thing. Again, the only contribution comes from x here. Again, it's 1 over square root of 2 squared. Again, it's 1/2. Right? How about the second diagonal polar, I'll call this diagonal, the second diagonal polarization pointing along the minus 45-degree axis? For that, I have to put minus here. I'm now using the second vector over here with a minus sign. Sorry, this is y. This is the probability that this photon is in the y direction. Right? Again, now we get minus 1 over square root of 2. But when we square minus 1 over square root of 2, we again get a half. I don't need to go through the last possibility. The probabilities for both of these in either the x or y direction is a half. So either photons prepared this way or this way, if sent through a vertical or horizontal polarizer, have a probability of 1/2 going through. That's not too surprising. I mean, that certainly follows intuitively, but it follows from the mathematical formulas that we've written down. Here's a new observable. We've now concocted a new observable. The new observable is not the polarization in the xy plane, but it's the polarization in the 45-degree plane. For example, we could define it to be plus for this polarization and minus for this polarization. This is a kind of rotation of the polarization observable. We can define a new observable. This new observable, we will say, is +1 for this and -1 for that. Can we make a operator for which this is an eigenstate with eigenvalue +1 and this an eigenstate with eigenvalue -1? Here's the polarization operator for the xy plane. Now we want to find the polarization operator for the 45-degree directions. Let's give that polarization operator a name. Let's call it this. there's a bit of arbitrariness. Do we call this having +1 and this -1, or do we call this one having +1 and this -1? But let's fix it. For the rotated polarization operator, let's say that this has polarization +1 and this one -1. Okay? Then we want a operator which has the property that it gives +1 times this, and the same operator should give -1 on this polarization. This would define a observable that's associated with polarization in the 45-degree direction. In other words, it would be the polarization observable for a polarizer oriented in this direction. Can we find such an operator? Sure. The easiest way is to do it using matrices. Let's find the matrix. Let's see if we can find a matrix which does that. I'm just going to write it down. I'm not going to bother finding it. I'm just going to write it down. Easy enough to explore around a little bit and find it. This is given by the matrix. The matrix which represents it is just 1, 1, 0, 0. Off diagonal, like this. Off the diagonal. Let's check it. Let's check that this polarization observable multiplies this vector to give back the same vector and multiplies this one to give minus it. All right, let's go to another blackboard. Let's see. Where shall we do this? I guess, well, I guess just over here. All right. So what this says is that the matrix 0, 1, 1, 0, that's the conjectured form for this polarization observable, multiplies this vector, but that's just 1 over square root of 2, 1 over square root of 2. To give, let's see what it gives. 0 times this is 0. 1 times this is 1 over square root of 2. 1 over square root of 2. Check that. Okay. So first of all, when it hits this vector, it gives back the same one. Let's see what happens when it hits the other vector. 0, 1, 1, 0. The other polarization looks exactly the same, except it has a minus 1 over square root of 2 here. So we write 1 over square root of 2 minus 1 over square root of 2. Now let's do this one a little more carefully. 0 times this element is 0. 1 times this element is minus 1 over square root of 2. And then go to the second row. 1 times square root of 2 plus 0 times this is just 1 over square root of 2. Notice that this vector is minus this vector. The vector we started with was 1 over square root of 2 minus 1 over square root of 2. The vector we wound up with was exactly the same, except with a minus sign in front of it. This is minus the original vector. So in fact, this operator, this matrix, represents the operator that we're looking for and represents the observable polarization, the polarization observable for the xy plane. Okay. Notice that there is no vector which is simultaneously an eigenvector of this polarization observable and this polarization observable. The eigenvectors of the vertical horizontal xy polarization are just x and y here. The eigenvectors of the 45-degree rotated polarization are the linear combinations x plus y and x minus y. There are no common eigenvectors, and this means that these two polarizations are incompatible. You cannot measure both of them simultaneously. In other words, there is no polarization experiment which can tell you simultaneously what the xy polarization is and what the rotated polarization. There are experiments which can tell you the xy polarization. There are experiments which can tell you the rotated polarization, but there's no experiment which can tell you both. because there are no simultaneous eigenvectors of these two. In other words, they're sort of like position and momentum, two incompatible quantities. If you know one of them, you can't know the other. If you know the other, you can't know the first. So these are another example of incompatibility. Next time, we'll explore more complicated states of polarization. We haven't discussed what happens if the polarization is along some arbitrary angle. I did not intend this to look like 45 degrees. If it does, I think it doesn't. But in case it does, it was not intended to be at 45 degrees. What happens if it's at 15 degrees and a perpendicular one, which is at 90 plus 15, would be 105 degrees? How do we describe that? What are the eigenvectors that describe it? And what is the polarization observable that describes it? The one thing you can be sure of is that it will be incompatible with the other two that I've already described. So there's no compatibility between the polarization observables in any two different directions. Oh, that's not quite true. Is there anything, well, if you rotate by 90 degrees, that's trivial. That just changes x into y. And of course, it basically just multiplies the polarization by -1. What had plus polarization becomes minus, never mind. As long as we're talking about distinctly different axes of polarization, then there are no simultaneous eigenvectors, as we'll see. And so they're all a mutually incompatible set of polarization observables. That's what makes this interesting. So far, notice that everything we've written down has no complex numbers in it. Why is that? Yeah, that's right. We're discussing a subset of the possible kinds of photons which are plane polarized. Right? If we put complex numbers in, then we're studying circularly polarized, left and right, and we'll do that also. So there's more polarization states than just those which are plane polarized. There are also polarization states which are circularly polarized, and we'll discuss that circularly polarized light next time. Yeah?
The probability of a photon getting through a polarizer seems to be observable.
Yep.
And yet you don't have an operator for it. You just draw them together and get.
Wait, excuse me. What I've been doing here is the observables for polarization. What are you saying?
Like for X has an operator in the X position, it's an information operator. The probability is to go out and get together without an information operator between
I'm missing your question.
Well, it seems like the probability is observable, but doesn't have an information operator.
Probability is not an observable. Probability you cannot measure for a particle. You measure probability by measuring many, many, many particles, but in a single experiment you cannot measure the probability. So probability is not counted as an observable. The polarization is an observable. You send it through a polarizer, it either gets reflected or it doesn't get reflected. A single experiment and you get a number. That number goes into your list and it's an observable quantity for each experiment. Well, let me, so I don't want to mix up language. Probability is not an observable. It's the polar. What's that?
It seems like you end up with a number after them got through.
I didn't mean to say you can't observe the probability. I said a probability is not an observable. That's a technical term, observable. It's a thing which you can measure in a single experiment. You cannot measure the probability in a single experiment. All you'll get is a +1 or a -1 with no way to determine what the probability is in a single experiment. So observables are things that you measure in a single experiment on the system, and you get a definite answer. There's no way to get a definite answer for a probability without doing the same experiment over and over and over again and accumulating lots of -1s and +1s. So according to the official language that we use, probability is not an observable, the polarization is an observable. That doesn't mean we don't, that we don't observe the probability, but to do so, we'd have to do a lot of repeated experiments.
I think what he's trying to say is something like this. You have something in a particular state that has been prepared. You have something.
One photon.
This p-hat thingy that you use, that you're going to observe, and then you have a third thing which is sort of, that's what the possible result that you're considering is. And then you get a probability by squaring that.
Whoa, wait a minute. Let's use language correctly. You know, the things that you can get, wait a minute, the things that you can get, the answers you can get are the eigenvalues. The possible answers you can get are the eigenvalues. You don't square the eigenvalues to get probabilities.
I just mean that you take the state, you hit it with the operator, the observable, and you form the inner product of that resulting ket with the bra for the particular result that you're considering the probability of.
You take the vector describing the system. Okay? You don't hit it with the observable. You just take its inner product with the eigenvectors, with two possible eigenvectors of the observable, x or y. And from these, you get probabilities by squaring. All right? So the role of the observable is to tell you, or the observable operator here, is to tell you what the possible values that you can get and which states have definite values. When you know which states have definite values, I might have begun with the operators rather than the states. I might have said, this is an observable. This is an observable. Here are its eigenvectors, and its eigenvalues are +1 and -1.
What I'm talking about is right there, okay? Where you write x over here on the, as the bra.
Here?
Over here is the bra.
Yeah.
Okay? It's really the complex conjugate of p plus of x using the eigenvalue equation.
Sorry, it's just a complex conjugate of the vector x.
Yeah, it's also the complex conjugate of the left side of the equal sign.
Yeah, they have it in this particular case.
So
yes.
in that particular case, you're also able to write it with the p in the same inner product.
Yeah, but you don't want to do that generally. You don't want to do that generally. You don't want to do that generally. What you generally want to do is take the inner product of the vector with the eigenvector of p. That's the general rule. Take the vector in question that you prepared, take its overlap or its inner product with an eigenvector of the observable, and square that to get probability.
Is observable the same, is that synonymous with Hermitian operator, or is there some situation?
All observables are Hermitian operators, and
And
all
the other
Hermitian
way?
operators are observables.
Okay.
Right. Right.
It's noting that you didn't have to choose numbers 1 and -1. You could have chosen 1.
Right. Right. I could have chosen 1 and 0, or I could have chosen.
1
Right.
and 59.
Absolutely. Absolutely. So there's an ambiguity in what the observer writes down in his notebook. But having chosen his convention to call one polarization 1 and the other polarization 7, you stick with it. Had he done that, the operator would have been, let's see, where is capital P? Then we would have written this and 7 over here. And the matrix would have been 1, 7.
An interesting case would have been 1, 0.
No, it's as interesting or as...
But the expectation value of that operator would be the probability.
in fact, it would be, yes. That's correct. That's correct. Okay? So we can actually make a correct statement using, all right, good. All right, so let me give you the precise statement which you just gave a special example of. Take this vector, okay? Take this vector, and let's construct out of this vector not this observable, but another operator, namely the dyad made like this. Okay? You understand what this thing is. This is a special case of the dyads that we spoke about before. Now take the vector that we're interested in and sandwich the dyad, this operator. Incidentally, this operator is represented by 1, 0, 0, 0, just as you said. Okay. Sandwich the vector, or use the vector is the bread, the salami is the dyad in between. Make a sandwich like this. And this, of course, is the probability because it's the inner product of psi with the eigenvector of the observable squared. Okay? There's another dyad we can make. The other dyad we can make is this one. This expression is the probability to find X polarization. This expression is the probability to find Y polarization. But neither of these two dyads happens to be this. What is this? This happens to be the difference of the two dyads. But I didn't, you asked the question, so I gave you a fairly complete answer, but it was not what I had intended to talk about. Does that answer your question? No. It answers it, but you may not understand it. No? Yeah?
For me?
Yeah.
Yeah, no, I was making a comment, not a question.
I know, but did you understand my reaction to your comment? Yeah, okay, good. 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 Okay. Yeah, your comment happens to be right, but it's only somewhat accidental. Yeah, no, but your comment is right. Your comment is right. This, you could have defined the observable this way, and then the expectation value of it would be the probability. Right. Right.
But the output would be 1 or 0, not the probability.
The output of the experiment would be 1 or 0. That's right. That's right. The output of the experiment would be 1 or 0. Right.
So I think to get to his comment, it seems like the real observable is the exclusion that the polarization is not perpendicular to what it's passed through, as opposed to that its polarization is what it's been filtered through.
Right.
You know that the only thing you know is that it's not 90 degrees off of what the polarization is supposed to be passing through the polarizer.
Say it again.
But if you're polarized on the y-axis, having passed through the polarizer, you have a 50% chance of being 45 degrees either way, 0%, zero
Right.
probability
Right.
Of being perpendicular to that polarization. So the observable really is the exclusion of the perpendicular to the polarization.
There's more than one observable that we're talking about. Which one are you talking about? You're talking about this one? You're talking about this one?
Talking about the x, y, yeah.
This one?
Yeah.
Well, this observable is the observable that's associated with a polarizer that's polarized along the xy axis. It's the observable that's measured by sending the photon through a polarizer that is either along the x direction or the y direction. Okay. That's what it is. Or if you like to be precise, it's the observable that's recorded by an observer who writes down +1 if it goes through that polarizer, -1 if it doesn't go through that polarizer. I don't know any other way to say it. To be very precise about it, the particular observable is identified with a particular apparatus for making a measurement. In this case, the apparatus is a polarizer, and the polarizer, let's say, in the vertical direction. The observable that's associated with it can be taken to be that thing over there. Of course, you could define it differently. As somebody said, you didn't have to define the eigenvalues to be +1 and -1. I did that for convenience. I could have defined them to be 15 and 42. That would have made very little difference to the discussion. I chose to define them +1 and -1 for symmetry reasons, but be careful with language. The language is that the observable is identified with a particular apparatus, and it records, or it has to do with the value of the thing that you would write down in your notebook after having let the system interact with the apparatus and then look at the apparatus. So it's a thing that has to do with one experiment, not a repeated bunch of experiments. And it's the little thing you record in your notebook, event by event. Good. Everybody happy? Good.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.